Hello and welcome back. This is Ethan7878. This is the second video in my series on programming, and today we're going to consider some sorting algorithms. Now, in terms of variety, there are a lot of ways to sort an array of numbers. So I decided to go over them in order from least efficient to most efficient. We'll start off with the simplest ones and get better and better over time. I won't actually give my exact code, it will be posted down below, but I will show off some pseudocode and some animations, so you should be able to recreate it yourself if you want to. Well, let's get right into it. Now, when you think of a sorting algorithm, likely the first thing that comes to your mind is just finding the lowest number and moving it to a second array in the first spot, and finding the next lowest and moving that to the next array in the second spot, and continuing on for all the elements. And this is very simple and fairly easy to implement, but it has a few flaws that I'll explain later. Now, I have this diagram here with our two arrays, the one that's unsorted and the second array that will be our sorted one. And what we do is we scan through the array and look for the lowest one, and in this case it happens to be 1, and we move it to the second array and we remove it from the first array to avoid counting it twice. And we carry on. We do the same thing with the second element and the third, and we have 4, 5, and 6. And the first problem that you can see with this algorithm should be very plain to see. It's that we've used two arrays to sort one array. And this is very inefficient with an idea called space complexity, because basically we've used twice as much space as we would normally need to. Now, for the second flaw in this, I'll go over to medley text that I'm using here for my pseudocode. So we're using the find lowest sort, and the time complexity, as you can see, is also O of n squared, so n being the length of the array. Now this means that if the array is 2 times longer, it'll take 4 times longer to sort. Now I have the pseudocode here. Make a new array, search the first array for the lowest number, add that one to the second array and remove it from the first, and then repeat. And as you can see, I've made just a brief version here using Java. So we look for the lowest one, and we initialize it at the 0, and we track where the lowest one is, and look for the new lowest one, add it to the second array, and remove it from the first. Another relatively simple sort that comes to mind is known as the bubble sort. And this one is very simple because all you do is you switch neighbors when you need to. So I have again a diagram up here with my unsorted array. It's completely shuffled. And what we do is we compare the first two values. So 5 is greater than 3, so 5 should come afterwards, and we swap them. So 3 moves to the front, 5 moves to the second slot. And we carry on for each element in the array, so 5 and 4 we swap, 5 and 1 we swap, 5 and 6 we don't have to because 6 is already greater than 5, so 6 should come after. However, 6 and 2 we should swap. And what we end up with here is the biggest value has sort of floated up to the end, which is why it's called the bubble sort, because bubbles rise. And we can carry on. Now that we know the 6 is the biggest value, we don't have to keep comparing it, so I've colored it in with this light-ish shade of pink. And we just pass through the arrow one more time. And this time the 5 floats to the top, and this time the 4 floats to the top, and the 3 floats to the top. And at this point the array is completely sorted, but just for the sake of completeness you have to pass through all the way. There are some checks that let you shave off a little bit of time, but the algorithm at its core, you pass in with the same amount of times as the array's length. Now moving over again to my pseudocode. The time complexity, again, O of n squared. So not very efficient in terms of time. If you double the length, it'll take 4 times as long to sort. And all you do is you go through the array and you swap the neighbors if needed, and you keep passing through until the array is completely sorted. So until no changes have to be made. And I've implemented this here, and I have my boolean has changed equals false. And if a swap is needed, has changed equals true. And if the algorithm finds that nothing has changed, it breaks, it doesn't even bother sorting the rest of it. Another simple sort that's among the basic ones is called the selection sort. And this is basically like the find lowest sort, but refined to use less memory. So we have our array up top, and we have the before and after, and what it does is it finds the lowest one in the array, which in this case is 1, and it moves it to the front, and it just swaps out the 3. So the 3 moves to the 1 spot, the 1 moves to the front. And now we know the 1 is sorted. So when we scan through looking for the next lowest number, we know we can ignore the 1. So the array is in effect split into the unsorted parts on the right side and the sorted part on the left side. And the sorted part gets ignored. Next we search for the next lowest one, which in this case is 2. And the 2 will go to the second spot and bump out the 6, so the 6 will go all the way to the back. Now the 3 is the lowest one in the unsorted part, and it's already in place, so we just swap it with itself, which basically means we don't move it. Same goes for the 4. And now the 5, we move to the 6's spot, and the 6 we move to the 5 spot. And the 6 is already in place, and we're done sorting that. Now over to the pseudocode, you'll see that the time complexity is still O of n squared. And the first thing that we do is, well, you can use a for loop as you're scanning through the array, and just the integer I that you're using to count can be your marker for where is sorted and where isn't sorted. But you'll see the nested for loops means it's I squared, or n squared, and all you're doing is you're searching the second half of the array for the lowest one, and then at the end you swap it into place. Next up we have the insertion sort, which is the last basic sort that I'll be covering, and in fact if you went to the same high school that I did, this is the last one that they actually teach in school. Now the way the insertion sort works is very similar to the selection sort in that there is a sorted part and an unsorted part. However, the way that the sorted parts and unsorted parts are handled is very different. Let me explain. Here again our diagram, and all it does is it marks the first element as being sorted. So it says, alright, the 4 is already in place, we'll just leave it there, and we move on. So the first element of the unsorted part, which is now the 6, gets moved into the sorted part, and we just put it wherever it needs to go to fit in correctly. So in this case, the 6 needs to go after the 4, so we don't even move it. Now the 2, we move on to, and the 2 is less than 6, so we move it in front, and the 2 is less than 4, so we move it to the front, and now the 2 is the lowest element in the sorted part. And we do the same thing for the 3, we just shift it down, and the 5, and the 1 gets moved all the way to the front. So you'll see it's a combination of like sort of a bubble sort in moving the elements down towards the front, and also smart management of your space by marking parts as sorted and marking parts as unsorted. Now to the pseudocode, you'll see that again I'm using I as my marker for the unsorted part, and all we're doing is we're inserting the number or the element at I into the sorted part, and we say, alright, if you need to swap, then swap it, otherwise break and move on to the next element. Now the tree sort, which is one of the first complex algorithms that I'll be showing off in this video, and the tree sort is a little hard to visualize by leaving the numbers in place. So for this one, you'll notice in the animation I actually drew sort of a bunch of bubbles all linked together with lines. So let me explain what's actually going on behind the scenes. In our array, we have a sequence of numbers, and what we do is we take the first one and create a node, which is basically, or a vertex if you want to call it that. And if you've already learned about graph theory, you'll know what this is, but if you haven't, it's basically a point that can connect to other points. And in the tree, this is known as the root node. And what we do is we feed in 5. So 5 becomes the child of 2, and it moves down just below it, and since it's greater we move it to the right side just as a visual indication. Now I have to feed in the 4. So the 4 is greater than 2, so we move it down to 5, but it's less than 5, so it goes to the left of 5, and we put it as a new node there. And we do the same thing with 3, and now 6 is bigger than 5, so it goes to the right of 5, and 1 is less than 2, so it goes to the left of 2. And this is our tree done. Now how do we pull out the values? Well, We take the 1 because it's the smallest one. We move on to 2, and then we go down the tree, and we find that 3 is the next lowest one, and then 4 and 5, and then we go down on the right side of 5 to 6, and we find that, and since 6 is the last one added, it goes to the end of the array, and we're done. Every node has been visited. The array is sorted. So the pseudocode for this one is actually a little more complex, but that's mainly because I'm creating the node object, so you can sort of skip over that. But you'll notice the time complexity is O of n times the log of n, which is much better than n squared. So it still goes up. It doesn't go up linearly. It's not O of n, but it doesn't go up in a quadratic function. It goes up in a log function, which is much better. So it uses a binary search tree, as they're called, to store numbers. And as you can see, I've shown the pseudocode for the node object. And down here is the actual algorithm. So we add each object to the top node and let it filter down to where it's supposed to go. And then we just pull all the nodes out of the tree and simply place them back into the array list. The next algorithm I'm going to look at is called quicksort. And as you can tell by the name, it's very quick. In fact, it's pretty much the standard for fast and very versatile sorting algorithms. And the way it works is by picking a pivot number, as it's called. And what it does is it splits the array into numbers smaller than the pivot and numbers bigger than the pivot. So it's mostly sorted. And then it quicksorts each half. Now I have a diagram here. And the way that the pivot is chosen in a lot of algorithms is it's just the last number of the array. So in this case, 3. And what we do is we move 3 to the center, and we move all the numbers smaller than it to the left and all the numbers bigger than it to the right. And the exact order may vary here based on what algorithm you're using to shift the numbers around. This is just shifting them left or right, not exactly changing the order or anything fancy like that. And now as you can see, 3 is already sorted because we know it's not going to have to move because all the elements to the left are smaller and all the elements to the right are bigger. So 3 is in place, 3 is sorted. Now we move on to 1 and 2. So 1 will be our pivot, and we move 2 after it because 2 is greater. And now 1, 2, 3 is sorted. Now finally 5 will be our last pivot, and 5 goes to the center, 4 goes to the left, 6 goes to the right. 5 is sorted, and then we quicksort 4 and 6, but since it's only one element long, it's already sorted, and the array is done. Now onto the code. You'll see it's very, very short because, again, it's recursive, so you just reuse the same code a lot. And the time complexity, again, O of n times log of n, so very, very fast. And as you can see in the pseudocode, we take the last number of the array as pivot, we split the array into elements that are greater than it and elements that are smaller than it. We put the pivot in between them, and we basically lock it in place. And then we take each smaller half and call quicksort on that. Next up, we have merge sort, which is also a very popular sorting algorithm. And the way that this works is by sorting smaller arrays and, you guessed it, merging them together. Now the process of merging two already sorted arrays is very, very fast. And this is what the algorithm takes advantage of. Instead of sorting a massive array, you sort smaller arrays and then merge them together. Now, instead of just cells with numbers in them, I like to visualize this one with bars. As you might have seen in the animation, it looks very pretty. And the way it works is we just take half the array, and we say, all right, half of that, and merge sort that. Well, it's only one bar, so it's already sorted. So we merge sort the next two, and they're already sorted. And then we merge sort the three of them together, and all we do is we move the first one to the third, and now those three first ones are already sorted. So we move on. Now these two bars need to be sorted, and these two bars need to be sorted, and then we just merge them together, and we have a sequence of 4 numbers that's already sorted for us. Now we merge all the first 7 together, and as you can see, it's already starting to look nice. We just merge sort the second half. I'm not going to show step by step for that one. And then we just merge the whole thing together, and there we go. Nice, neatly ordered. And the pseudocode, again, as you can see, it's very short because it's recursive, so you can just reuse the same code over and over. And the time complexity, again, O of n times log n. So a lot of recursive methods of doing this tend to have n times log n just because of the way the math works out. So we split the array in half and we merge sort each half and then merge the two halves back together. And as you can see in the code, that's pretty much all it does. Now I didn't go into too much detail in the merge method because it changes a lot based on whether you're doing it in place or out of place. So if you're merging it into a different array and then putting it back in, or if you're merging it in the same array, there are ways of doing each. Personally, the one that I did was out of place just because it's a little simpler. Next up, we have actually the most recent one that I learned about called timsort, which has become kind of the standard for very fast sorters, even more than quicksort. It's used in a lot of standards, for example, Python and Java. Programming languages tend to have it built in. And the way it works is it takes advantage of just random chance, because usually in a randomly generated sequence of numbers, there will be at least a few elements that are already sorted, and timsort takes advantage of that. So we start off by scanning through the array, and we take the first element and mark it as the start of our run, and if the next element is bigger than it, we add it to the run. If not, we don't. So the next element bigger is that one, and we just put them all into a single run, and that will be one part of our sorted array. And we carry on, we generate ever smaller and smaller runs, and as you can see, the last ones are very, very short, because at that point there's not very much left to scan through. And now we do something very similar to merge sort. We just take two runs and group them together, and we take the next one and merge it in, and keep merging each run in until we have a sorted array. Now, as you can see, the pseudocode for this is a little more involved, but that's just because you have to implement an algorithm for finding the runs. And so I create my array list of values, and I create a 2D array list for all the runs that I'm going to store. And for each run, I start it off, I look through the array to see if I can add the next element, and if I can, then I remove it and I add it to the run, and then I just add the run to the array list. Now, as you can see, to merge them all together, all I do is I start off with a sorted part, and then I just merge each run into the sorted part, as you can see in my loop. So it's actually a very genius algorithm taking advantage of just random chance already doing some of the work for you. Next up on the list is the radix sort. And this is a very pretty looking algorithm if you ask me. And in fact, I think it might be my favorite just because it's so magical. And this algorithm actually works without comparing any two elements in the list, which you might find confusing at first, but once you understand how it works, it'll hopefully make a little more sense. Now, as you can see on the bars, I've put them into binary numbers because if you use base 2 for this, the patterns that emerge are a lot more evident, which is what I'm going for. And so you see, it's all 4-digit binary numbers from 0 to 15, but the bars lengths are 1 to 16, just for the sake of demonstration. Now what we do is we look at the last digit, or the bottom digit, of each number, and we put the number into a bucket corresponding to that number, and then we take every number ending with 0 and put it into bucket 0, every number ending with 1 putting it into bucket 1, and this is what we end up with after one step of doing that. So as you can see, I've highlighted them in red. All the zeros are on the left, all the ones are on the right. And next what we do is we do the same thing but for the second digit. And this will mess up the order for the first digits, but that's fine because they're already more or less sorted. So do the same thing with the second digit, and you might already see some patterns starting to form in the height of the bars. Look at where the bars end, and you'll see some lines actually forming. And this isn't by chance, this isn't random. This is actually this is a sign of how the algorithm works. And it'll become a lot clearer once we move on to the third digit. and you'll see two distinct lines forming there. And you see the bottom two digits are already getting scrambled a little bit, but there's actually a pattern behind that too. And now you'll see two very distinct lines forming. And I bet you'll be able to figure this out on your own, but I'll explain it a little bit later. And finally, we sort the top layer, and we have our nice sorted array with a straight line. Now what we have in the pseudocode, you'll see the time complexity is O of n times k. So as the length of the array increases, the time to sort it increases linearly as well, times a constant k. And we place items into buckets corresponding to their last digit, we take them out, and we repeat for each digit. And just as an illustration, say you have the numbers 99, 100, 199, 200, 299, and 300. Well, sorting by the last digit, you would get 100, 200, 300, and then sorting, and then in the second half you'd get 99, 199, 299, which gives rise to all these interesting patterns. And then eventually, once you got around to sorting by the first digit, which in this case you'd have to put in a 099, but once you did that, it would all fall into place. So I just have my array list of integers with buckets, and that's where I throw all the numbers in, and then all I do is pull them back out and put them into the array list. And this never actually compares two elements together. It never directly compares two elements, which is very ingenious. It saves a lot on computing time, and that's why the time complexity is so low. Now, last but definitely not least, we have the gravity sort, also known as the abacus sort or the bead sort. And as you can see in my graphic, I've changed pace. Instead of representing them in a list or as bars, I've represented them in an abacus. And each bead on each row represents the number related to that row. So as you can see, 9 has 9 beads, 8 has 8 beads, etc. And what we do is, for each column, we drop each bead to the lowest possible level. So on the far right, there's 1 bead in that column, so it'll occupy the bottom spot. And as you can see, the row that had 10 now has 9, and the row that had 5 now has 6. Do that for the next row over, and each row that had 9 now has 8, the one that had 2 now has 3, etc. And we just do this for each column. And what you'll see is that we get a nice staircase forming, and by the end of it, our array is completely sorted. Now these numbers are completely different from the numbers that we started with. It's just that by rearranging imaginary beads on an imaginary abacus, we ended up with the same numbers back again, sorted in order. And this algorithm, just like the radix sort, never actually compares two elements together. Now moving on to the pseudocode, you'll see that the time complexity is even better than the radix sort. It's O of n plus k as opposed to O of n times k. And as you can see, I reiterate here, imagining beads on an abacus with the number per row representing an element in the array. And for each column, we drop all the beads, and then we count the beads back to get the numbers back. And it's actually a very, very simple algorithm for not using any if statements. And as you can see, just for the sake of making it look nice, I start from the right and work my way to the left. Although you could work your way from the left to right. I just did this to look nicer. Well, that's all of them, right? Not even close. There are so many ways to sort an array of numbers, and that's why this is such an interesting field for anyone who likes computer science. This is definitely a topic that I'll be revisiting in a future video. I really hope you enjoyed watching the video. If you liked it, then you make sure to hit the like button before you leave. If you have any feedback, leave it in a comment down below. If you want to see more videos like this, you can look at my channel or hit the subscribe button so you know when I upload next. As always, my full code will be posted down below at a GitHub link, and I'll catch you next time.